additional sensors and map those sensors and make calculations on those. You get a large-scale evaluation of it, so you can collect all the historical data and you can make sure that your models and your learning algorithms, whether you're using online learning or whether you're using static learning from snapshots in the data, are correct, because you can look at the actual historical data. And the embedded systems, at a certain point, you have to throw that data away or the actual system will just shut down and you'll have a robot that's just dead in the water. And then you can monitor and control systems. So you can do things like, hey, we have a power sensor. How much power is this robot using? Do we need to use this amount of power at this point? And you can kind of mediate those kind of challenges. So I think bringing SLAM into the IoT space is ideal. And I think it's more than interesting. I think it's a very lovely problem. And I think because it's so complex, I think there's a lot of room for growth. So if you're interested in this kind of research, I advise you to explore it. So what do we have right now? So if any of you are familiar with robotics in the robotics space, you're probably familiar with ROS. So ROS is the de facto standard in open source robotics. It's a lovely platform. I've used it. I enjoyed using it. However, if you get into large level distributed systems, ROS has some challenges there. And ROS is an operating system kind of atmosphere, so it's not really like a plug and play kind of environment. You really have to commit to ROS. And I think it's not actually real time. It's near real time, but it's not real time. So that's another aspect of ROS that you want to take into consideration. And some of the low level tuning are a little bit more difficult depending on your implementation of ROS. So those are some challenges, but ROS is a great system. It's been around for quite some time. It's open source, which is free and wonderful. So I advise people to explore it. But I think with IoT, I think we can do something better, and I think we can do something bigger and more encompassing. So that's where I think we need a framework with Kafka and Spark Streaming. So obviously I'm a little biased. I work at Spark STC, so Spark Streaming and Kafka were the go-to, but I still think it's a great platform and I think it's a great introduction to the cloud. And I think there's a need, because I've seen some Jira about having Kalman filters and some of the stochastic gradient descent algorithms on Apache Spark and on other platforms. And I think this is the time to do it. I mean, we're coming into an area where robotics is going to be part of our lives, part of our everyday lives. And so we should be ready. So this is why I started working on this framework. So I did a very simple approach because this is a very complex problem, and I figured starting simple was always best. I did the EKF, which is an extended Kalman filter. So this is a matrix-based update estimation. It has a state matrix that is constantly updated based on like various covariance matrices and other matrices that are associated with it. It's the nonlinear version of the Kalman filter. So if you're familiar with the Kalman filter, then you know that it's the standard in this type of automation. For our simulation, I chose the Turtlebot. He's a standard robotics research bot, so a lot of robotics labs use the Turtlebot because he's relatively cheap for a robot, but he's pretty cute. So, and then there's the Gazebo Simulator. There's another open source tool which simulates the sensors, the feedback, and the movement of the robot. So you can implement your algorithms and then run them in the simulator to test how they actually work. Obviously, this is not 100% because in real life you have mechanical errors and physical errors and hardware errors and actual physics of a problem. For instance, going up a slope, you're going to get different readings than you would on a flat surface. So you have to take real things into account that you just don't take into account on a simulator. But still, it's a good starting point. Specifically, the Turtlebot is known for odometry errors over time. The accumulations of errors in the Turtlebot are known to be greater than standard. Not bad, but larger than standard. So if you're not familiar with the Kalman filter and the EKF approach, like this is a very simple model of it. Obviously, all the mathematical computations are not included. The matrices are not, verily referenced. But if you look at X hat, that's a matrix that is updated, and at each step, you can see that there's a prediction made, and then we compare the prediction to ground truth, and then you update your measurements based on the difference between those two, and then you have another estimation of state, and then you keep updating your estimations. What is not included in this particular graphic is the landmarks that you're computing. The landmarks are included in your state matrix, and those grow continuously as you accumulate additional landmarks. And if there's an error, then you have to go back and update a previous landmark. So that is definitely computationally intensive, and it grows with the number of landmarks. As long as your space is small, as I've said before, you won't have a problem with it, but as your space grows, definitely there will be computational challenges. So here's our turtle bot. And as I said, he's also very cute. You noticed his very sleek profile there. And he will attempt SLAM, so I'm answering his question for him. So this is the framework. So this is just a use case that I was exploring. So what I did was I got an IBM soft layer cluster, which is available to us at IBM. If you're interested in clusters or hosting servers, there's soft layer, there's Bluemix. IBM has a number of different solutions for this kind of problem. But we did it on a basic, Ambari yarn install and HDFS store for storage. I ran Spark and Spark ML and Kafka Spark Streaming. So Spark ML is running behind to do the learning and evaluations, and it's doing it in sort of an online format. There's a slight built-in delay that I used based on the mechanical features of the particular turtlebot, but we'll go over that in a few seconds. So this is the basic setup of the cluster. I had a management node, which had a multi-threaded producer. So I assigned each sensor a thread, just because if you're running on a distributed cluster, and let's say you want to partition your cluster by the type of sensors, which you could do if you had maybe a swarm of robots, I thought this was an easily scalable way of doing that. And in practice, on the simulation, it ran really well. So you have the sensors, then you have your mapping agent. And in this case, our mapping agent is Gazebo and MATLAB to actually draw the maps. And then we have Spark Streaming and for the consumers on those two nodes. So they're consuming the sensor data and then processing it. And then you have a Kafka producer to push data back out to the simulator to update the robot's movements. The Spark ML and Spark ML Analytics are on the learning part of its algorithm. So the learning part is actually a very simple algorithm that we'll go over shortly. So the idea is to have a really high-performing plug-and-play cloud for smart robotics, drones, and intelligent systems. And I want it to be tunable with tunable interactions for both scientists and industries. So, I came out of academia, so the first thing that happened when I brought this to my supervisor was, how will this make us money? How is this useful? And my answer was, I don't know, but let's build it and find out. So, and that's my answer to everything usually. But so I built it, and I think after building it, I can definitely see how if we put this in the mainstream, if we allow cluster implementation, if we said, hey, whatever sensor you have, whatever robot you have, you can plug it into our cloud, and we can make it happen in a really short amount of time. It means you can use ROS, and you can spend 20 hours tuning a ROS implementation on a specific platform that will not scale, or you can use our cloud that already has the scaling built in, that scales seamlessly and integrates to as many robots as you need or as your cluster can actually support. So in this case, we have our turtlebot, it's Kafka, Spark, Streaming, Analytics, Computation. You just have the communication circle that's happening. The data that you're getting from the turtlebot is the odometry, which is pose and orientation data for each movement of the turtlebot. You have your laser scan data, which happens every 30 milliseconds. And each of those data has over 1,200 points. So you have the scans at about 43 degrees that you get 1,200 points for, all the ranges that it gets back, so how far that laser beam went. In the case that a scan is out of range, you drop that laser signal. And this is only for one robot. So as you go on and get more and more data, you can see for 1,200 data points for each scan, you're going to get a lot of data. So this goes into the big data side of things very rapidly. There's no question. You could run it, I think, on an embedded system at about 500 iterations. I couldn't finish. So when I brought it into the cloud, it was relatively seamless. So we have EKF, which is primarily calculated using the matrix operations. We have our distributed raw sensor data on Apache Kafka. We have our RDDs and Spark ML for the computationally intensive part of it, and for storing all the data. Once it's generated, we can create an RDD and store that data. We're also using data frames in the Spark ML corner when we pull in the data from the online algorithm, process it, and then push it back out. And again, it's faster than embedded systems. You get real-time, near real-time or real-time sensor messaging, easy integration and scaling, and then you can retain your data. You can improve over time, something that you cannot really do with an embedded system. So some of the things that were a little bit different in my implementation from what I saw from the standard implementations were multi-threading the producers. And then I scaled it to the hardware time. So in a lot of the implementations that I saw, the producers were not multi-threaded, and I believe Kafka is backed by a thread pool in Java, at least in the Java API. But in addition to the thread pool, you may want to scale it to do your hardware timing, because if you have a lot of sensors coming in at the same time, and you can run them in parallel, but there's no need to do that if, let's say, your laser comes in every 30 milliseconds, but your odometry only comes in every 40 milliseconds. You have a 10 millisecond difference there that you can scale those threads and have a lot better processing speeds. So this is something that I implemented that I thought was very useful, and I did see a time improvement after doing that. You can share instances of the producer, so that was something that happened here. That's just a Kafka feature. And then if you want to partition it by sensor analysis or by like computational history data or in a snapshot way, I mean, this is easy to do on the IoT cloud. So this is the Apache Kafka implementation. This is just a glimpse of the code for multi-threading the producers. This is on the local simulation that I set up. You can see it's running here, and it's running the two topics, the odometry and the laser. Some of that data is cleansed and scrubbed before it's actually pushed into the producer. Then you have your Spark streaming, which replaces the Kafka consumer. So normally you would build a Kafka consumer, and initially I did because I didn't realize Spark streaming would actually take over the consumer's position, and then I found that out and didn't need the Kafka consumer. But it's really good because you have the write-ahead logs, you have adherence to the fault tolerance policies in Spark streaming. And then in the new edition of Spark streaming, you have your direct stream that doesn't use the receivers, which is very nice because in the older versions, it was a little bit more difficult to get the low-level Kafka data, which includes the producer topics, like is this an odometry send or is this a laser scan send? And then in Spark streaming, you have the micro-batch processing and then better integration into the analytics. I know Kafka recently came out with a Kafka streaming to do their analytics, but I think Spark is already doing that, and we're already there, so it's always nice not to reinvent the wheel, at least for me. So this is Spark streaming. This is just a sample of the code from the Spark streaming. You can see all of the different things happening there. Some of the property settings are not available in Spark streaming that you would get with the Kafka consumer, and you have to take that into account. And again, accessing the low-level topic data is not necessarily native. You have to pull the metadata out of Kafka. So that's a couple extra steps that you wouldn't need in the Kafka consumer. But again, you have access to the Spark and the streaming analytics, which I think is a huge advantage. Let's see, the ransack algorithm that I mentioned earlier. So the learning algorithm, it takes the landmarks that you get, and basically it samples some given number of samples of landmarks and decides if this creates a line or a wall in the real space. So this is an iterative algorithm that goes on continuously throughout SLAM. And then in addition to this, you have your updates happening on landmarks that you previously got wrong. So from this, I piped it from Spark streaming into Spark ML. And so you can see the Spark ML example here, and you can see the parameter settings, you can see the iterations running. So it's a pretty smooth integration process, and you have all your streaming analytics available to you right away. So some of the key challenges in this were network latency. So embedded versus framework. Obviously, if you're running an embedded system, you have far less latency than you would have on a distributed system. So you have to take that into account. But again, I thought that staggering the feeds was very useful and improved latency times and throughput immensely. You have matrix computations and updates to large matrices. So in EPF, you're running Jacobian derivatives, you're doing inversion, you're doing transposition, multiplication, addition, you're doing Gaussians. So these are all mathematically intensive and CPU intensive functions. So you really have to build something to optimize for that. SparkML is not necessarily optimized for that yet, although SystemML is. So I think what we will be doing in the next library update for SparkML is adding these matrix computational functionalities and optimizing them for rapid speed. So coordinating movement with computation, so getting the times right, you have to throttle the movement just so that you know exactly how long each step took and how much CPU time was used at that step. And just doing your simple SLAM, like evaluation of errors and landmark data. So by the time I was done, it was about 4,000 lines of code. But again, I did it in Java just because that's what I knew. And Java's very verbose, so if you want to subtract 1,500 lines from that, I think that's fair. I thought the Java Lambda documentation could be better. Java 8 has the new Lambda architecture, which is great and makes things a lot less verbose, but the documentation on it is a little sparse. Getting Kafka topics is a little bit difficult. And then some of the things that if you're thinking of building something similar is communicating with a simulation, you need a specific class to do that. So I'm using a MATLAB bus to push the data through the simulation back to the code in Kafka. But I think in the future we will be building a solid communication class to the simulator. So this is just a measurement of network latency in the throttled simulation. The timing was kept pretty static just to make sure that the delays were, not the messages or things like that. And these are just the number of iterations. So at 10 iterations, you can see we have, pretty straight line in both. It's basically the same, not a huge difference between the embedded and the cloud system. But then you have the iterations at 200, and we see a completely different thing. So we're doing simulations on one side, and we're doing file on the other, just to make sure that we don't have to account for latency and this timing. But this is just on the computation alone. You can see the growth on the embedded system is a lot faster, and it was not even able to complete all the iterations the first time it tried. So we had to keep going in and optimizing the embedded. So you have to get into things like sparse matrices and dropping some of the computations that are too intensive and staggering them on an embedded system. You didn't need to do any of that on the distributed framework. It just ran, and it ran smoothly. So this is, again, the Turtlebot. Again, he's also being cute here. This is actually what he sees. He has a 3D camera, but what we do is we take the 3D point cloud data and we convert it to your Cartesian coordinates in an XY frame. So I get actual XY coordinates back from the laser scan, I'm using quotes, because you actually see this. So again, if you want to get into the computer vision side of this problem, this bot is more than ready for it. That glass window in there, obviously you would not get a laser feedback from that. You would go out of range on that glass. And things like differentiating between that garbage can and the carpet, which easy for a human, very, very difficult for a robot doing a computer vision task. So we ran 500 iterations. The embedded system only got to about 300 running SLAM. The framework completed all of its 500 iterations with the expected growth. So we expect growth, like an exponential growth with the number of landmarks. And you can see that curve here, but the embedded system couldn't complete it. I think it stopped around 300. So it was interesting. So if we get to iterations, we run about a similar number of iterations, and then this was mapped on the MATLAB from the simulation data. This took approximately 2 minutes on the embedded system and about 30 to 40 seconds on the framework. So again, a significant time improvement with relatively the same data. So some of the benchmarks that I still need to go into are the ransack conversion on Spark streaming batches. We want to make sure that convergence is fast and optimal. And also need to measure the latency between the Kafka brokers. And we want to look at the batch processing throughput in relation to the processing time, just to make sure that those two parameters are optimized. Oops, okay. These are some of the points that you want to take into mind if you're doing this yourself. So you want to use sparse and distributed matrices and SparkML, and that's something that we're going to implement for the libraries. Separate threads for the Kafka producers. I guess one of the key points are I'd like to have a full library for this, but also scheduled feature extraction to minimize accumulated error in the long runs. So if we get to a point where we see the error is at a certain level, we can say, okay, we need to update our model at this point now and not wait. And if you're doing an online algorithm, that's not necessarily, you don't necessarily have to worry about that. But if your model gets to become too inaccurate, then you want to have something that triggers updates automatically. And then some next steps, we want to expand the stochastic analysis, in the libraries for Spark, improve accuracy and precision, do some path planning, incorporate swarms and particles. I'd like to see swarming bots and particle analysis for this. And we want to build a complete robotics library in Spark and do some further scaling optimization. So these are all things that will be happening, but are not happening right now. Oh, okay, they're happening right now, but they're not ready for you right now. And just the takeaway for this is, we have billions of things that are going to be connected to the cloud soon. And I think this is going to be the future for robotics in particular, because we can integrate the robotics data not just with the environment, but with things in your house. Like let's say you have a robot that can go and take milk out of your fridge or maybe do some cooking in the future. You want to have all of those things integrated so that the robot knows, hey, there's no eggs in the fridge because the fridge has sent a signal saying we're out of eggs. If you like to cook eggs. Okay, so I have a simulation that I prepared, and this is just running in Gazebo. So this is the Gazebo simulation of the turtle bot. And so this is the EKF SLAM algorithm that I'm starting up here. Yeah, he's good. And then these are the Kafka producers. So this is Spark streaming running. Then we have Kafka running on the producer. This is the MATLAB bus that buses the communication to the simulator. So it's not actually part of our code. The current library for Gazebo Simulator is written in Google Protobufs, and it's a C library. So I didn't have time to write a new communication for that. Is it running? Ah, yeah, there he is. So this is full screen. You can see the little bot moving. And so this is happening in real time. It's slightly throttled per iteration between the move. There you have some very simple collision detection. Basically, the robot says, hey, I'm within X amount of some landmark. What should I do? And at that point, he spins and goes into a new direction. So this is him. And I like to mess with these robots because they're funny. So sometimes I do things like drop balls in front of them. So he's pretty cute. He'll go to the ball and then he'll move. He'll say, ah, there's a thing there. So if that were like a person or a human and you were doing SLAM navigation in real time, you would also want him to not mark that as a landmark because the person would move. In this case, it's just a big giant ball, so it doesn't move, but he moves in real time and he avoids the walls. And the maps I showed you earlier of the space are him mapping the space in this room. There were some other objects. I don't know if you saw those, but I dropped a bunch of objects in front of him just because I thought it was funny. And he continued to move through that space. Let's see. So this is obviously the Spark streaming running, going to the RDDs, and this is running mostly locally because it's such a small size, I can still run it. But again, there are a number of iterations here, and the number of seconds that I'm running it is very small, so you don't have that boundary that you have on a robot running in real time for an extended period of time. Let's see. And as you can see, some of the scan data coming in, and this is how rapidly it's coming in. This is the producer producing the output. I just piped it to the output just for fun, I guess. Well, to show people, too. That was that. I had a reason. And I guess besides that, just wanted to say thank you to the Hadoop Summit, thank you to my team and to the supervisors that allowed me time to work on this project because it was very time consuming. I did it in a very short amount of time and it was still interesting and fun and I can't wait to see it in Spark's libraries. If you have any more questions after the Q&A, this is my email information and I'm in San Francisco, so I guess any questions?
Is it vanilla Spark that you installed there?
Pardon?
Is it like a pure Spark? Or
This is a pure Spark implementation. Besides the Kafka part of it, it's pure Spark. So that was something that was insisted upon by my supervisor, which I initially balked at because I knew that it was going to be a lot of coding. But you can actually do this with Java and then pipe it into like a Spark streaming and then pipe the data into a Java backend to do like optimized matrices. But I think in the new libraries that we're going to release, you won't need to do that. You can do a pure Spark implementation like this one. This one, again, is about 4,000 lines of code. Python, you might get it down to like 2,000 or 2,500. Yeah.
I guess my question is, you have like Linux stuff as well,
Soft layer, but yeah.
Yeah. So is that what you use?
Yeah.
Oh.
Yeah. Yeah, this is all like, this is the embedded implementation. We actually run this on a soft layer cluster and actually have all of it piped to the different management nodes and things of that nature, so. Oh, sure.
Do you plan to open source your code so we can replicate your experiment?
I plan to develop the libraries in Spark so you can replicate it in maybe 300 or 400 lines of code. Yeah. Yeah, I think it'd be awesome to have Kalman Filter and extended Kalman Filter in Spark. That's kind of the dream for me.
When you laid out your three software machines, you pretty clearly showed where all the various entities were part of your system file, but I didn't see what the brokers were. What were the brokers?
The brokers are, you have your main Kafka producer, and then the two management nodes are the brokers. So they're brokers as well as being part of the cluster for like Spark streaming and things of that nature. So they have more than one function.
So you had two brokers.
Well, you have three altogether.
So you had one on each machine.
You're right, exactly. Because you can consume without using a Kafka broker on the Spark streaming ones, but you can't push the data back. So you need an additional broker on those machines to do the pushing the data back to the simulation. Time is up. Okay. All right, thank you guys. Have a great day at the conference.